I'm going to hand it over to Nina Balk. She's the AIF director, and she has a few words about AIF and its mission here at NC State.
Thank you, Jordan. So yeah, my name is Nina Balke. I'm the still relatively new director of AIF. I started last October and took over from Dr. Jacob Jones. And this is actually my my first workshop. So I'm very excited about it. I was very intrigued by the idea of having a combined workshop between AIF capability or characterization techniques and instruments we have, together with a company who provides cameras in like we see today for the Titan. So I think it's a really good synergistic effort, and it benefits everyone involved, and we can provide this workshop to all of you. Since I'm the new director of AIF, and some of you might not be familiar with the AIF, I want to spend a few words on it. And as you can see on the slide, and I'm going to read this off, the AIF is the largest shared facility at NC State. It's housed in the College of Engineering. And our AIF mission is to enable and lead state-of-the-art research through the acquisition, development, maintenance, training, and access to major analytical materials and biological characterization and instrumentation. So that's a mouthful, right? So what it means in a little bit more detail here, some of our mission is enabled by building next generation infrastructure. In recent years, we have really invested a lot in biological and soft matter research, and also state-of-the-art computed tomography. So these are some of the newest capabilities we develop. And another big part of our mission is education and outreach. So we're providing workshops, short courses, open houses, tours. Anytime you're nearby, let us know. We can schedule a tour. And also, we provide by now a lot of online content due to the pandemic. So that's one of the silver linings. There's a lot of resources about AIF and the different techniques we have online. This here is my favorite slide because here we can brag about what all we have, right? So it's just written down, no images because the time didn't permit it. But you see we are very strong in microscopy. We have very varying SEMs. We have 2 focused ion beam microscopes, 3 TEMs, so one of them you see today. There's also 2 X-ray tomography microscopes. One is a micrometer scale, and the other one's nanometer scale. We have expertise in surface analysis, XPS, TOF-SIMS, Raman, diffraction. We have diffractometers. We can perform EBSD or the electron diffraction in the TEM. And then, as I mentioned, one of our core capabilities we're developing is for the biological community, where we have bio-EM sample prep, and we have different capabilities there, like a freeze fracture or high pressure freezer. I really want to introduce to you the staff at AIF because they are true experts in the characterization techniques we provide, and we are here to help you. This can have various shapes. We can either train you on a specific instrument. We can educate you about certain characterization techniques in form of short courses, or you can hand over your samples and we will do the measurements for you. If you need support in your research, just contact us. We're here to help. And with that, I think I want to let you get to what you came here to do, learn about TEM. And I'm looking forward to receiving feedback about this workshop, and also perhaps see some of the people online as future users of the AIF. Thank you.
To get started, I want to introduce my colleague. Anna Pakzad is the diffraction product manager at Gatan. Formerly, she was an application scientist. She worked with our imaging cameras, but as the market and the need for advanced diffraction techniques has grown, we wanted to employ Anna to help grow that line of the business and also help facilitate the research needs of that group. So with that, I'll hand it over to Anna Pakzad, who's our diffraction product manager. Anna, you can take it from here.
Thank you, Jordan. You can hear me okay?
Yes, we can.
Okay, perfect. Hi, everyone. And thank you for attending our workshop in person. And also, I see we have people online attending. That's great. I apologize I couldn't be there in person with you, but hopefully we have some interesting material and demos to show you this afternoon, as Jordan said, talking about diffraction and specifically 4D STEM. So let's jump right in. Just before I go to the content, Parker has asked me to remind everyone, if you have any questions during the presentation, please submit them via the question pane. If there are technical problems, she will try to help you resolve those immediately, and then I will get the questions at the end of my presentation. We will do the same thing during the demo session. Okay, so as Jordan was saying, diffraction imaging is one of the most common and important capabilities of any TEM. Usually we are looking at crystalline materials. When we pass the electrons through the sample, of course, electrons diffract, and we try and image them. And to do so, if you look at a ray diagram in a transmission electron microscope, in between the specimen, in between the objective lens and the imaging plane, there is another plane that is called the backfocal plane, where the diffraction images are formed. And so what we do for diffraction imaging is we use the projector lenses and we project this plane onto the camera, and we image the diffraction patterns. Now, there could be different modes and different ways where you set up the optics in the microscope to collect a diffraction image. You could be in parallel mode condition where you hit the sample, and that's where usually you get spot patterns, or if you have a polycrystalline sample, you would get ring patterns, as I'm showing here. If you have an amorphous sample, you wouldn't see diffraction reflections, as I'm showing. And if you are, your beam is converged as it's getting through the sample, so there is some kind of angle, a convergence angle, then instead of looking at spots, you will get discs, as you're seeing here. So that's called convergence beam electron diffraction. Each of these will, of course, tell you a lot about the crystalline structure of the material. Looking, for example, in the contrast reading, see that this can also tell you about strain in the material, if there is bending in the material. So there is a lot of information inside diffraction images, and you can use that information to learn more about what's going on in the structure. So one of the methods to collect these diffraction images and then analyze them is called 4D STEM, and that's what we will be talking about today. Basically, what we are doing is we run the microscope in STEM mode, and we have a pixelated detector or a camera like the one view that is installed on the microscope. And at each pixel position, as we are scanning the probe on the surface of the sample, we collect a two-dimensional diffraction image. Normally, and most commonly, people scan the surface of the sample in a 2D array. So you have 2 dimensions on the spatial domain, and then you have a 2-dimensional diffraction image at each pixel position. That's why this technique is called 4D STEM. So you get 2 dimensions from scanning and 2 dimensions from the diffraction pattern. Now, depending on what else you have installed on the microscope, you may also have a STEM detector inserted and collect that signal simultaneously as you're collecting the diffraction data, but you don't have to have that inserted during data acquisition. You need a STEM detector to set up the experiment and find your region of interest, but once you're done, you can actually retract the STEM detector so that you can fully illuminate your detector, your pixelated detector, with the diffraction signal. And then we will show you during our demo, once you have the 4D STEM data, you have all the information to reconstruct from your 4D STEM data any kind of virtual dark field, bright field, or annular dark field images from the data. So that's why you don't have to have the STEM detector inserted. Okay, So this is the concept of 4D STEM and why we call it 4D. Again, if you look at the image, this looks like a high resolution STEM image. If I zoom into my STEM image, you will see the pixels, and then at each pixel position or at each probe position, you have a two-dimensional diffraction pattern, and this constructs your four-dimensional data cube. This was a very quick and brief introduction to the technique. If you need to, or if you're interested to learn more, we have several resources on Gatan website. We have a 4D STEM technique page where we talk about the basics of what it is and how it's done in the microscope. We also have specific technique page for strain mapping and differential phase contrast imaging, and we also have made several training videos on how you can use digital micrograph to process 4D STEM data sets. So I really recommend, if you're interested in this technique or if you're new to this technique, you can go to our 4D STEM technique page, read through the material, and also go to the media library and watch the videos to learn more how you can process the data. We also have a large list of publications on 4D STEM technique, which is examples of high impact, usually, as you can see here, Nature, journals where our customers are using our equipment to collect 4D STEM data and analyze their samples. Another very, very good resource I like to recommend this to people is this paper that was published a few years ago by Colin Opus, one of our great customers at STEMx. So he also goes into details of what 4D STEM is, and he also explains briefly and have several references for each of the techniques or each of the types of experiments that can be done with 4D STEM. So this is also a good resource to read through to learn more about 4D STEM. Okay, so in order to do a 4D STEM experiment, as I was saying, you need a pixelated detector or a camera. And with Gatan, the tool that allows you to collect 4D STEM data sets is called STEMx. So that would be this box that you see here. I'm not sure if you guys had a chance to see it when you, the ones who are there, when you were in the lab. What this box does is that it hardware synchronizes your pixelated detector, so this can be any of Gatan cameras, to the scanning coils of the microscope. So we collect hardware synchronized 4D STEM data sets at high speed. The STEMx also comes with data acquisition and data processing software, which is in digital micrograph, and that will be the main part of the demo, where we will show you how we set up the data acquisition and then show you how we can process the data once you have it in digital micrograph. STEMx is compatible with all of our modern cameras. So here you can see one view is what is installed at NC State right now, Rio camera, K3, which is our direct detection camera, and also recently we introduced the Stella camera, which is a hybrid pixel detection camera, and I will talk about this one a little bit at the end of my presentation. STEMx is also compatible with all of our cameras that are installed behind the GIF. So you can also do filtered 4D STEM with the cameras. For example, K3 or Stella can be mounted at the end of the GIF, and you can use the STEMx to collect 4D STEM data sets, filtered 4D STEM data sets on the back of a GIF as well. Okay, so right. So as I said, it's very simple to actually set up your experiment and acquire your data using the STEMx and the digital micrograph software. What you do is you use the SI acquisition panel You select a seabed signal as the signal that you like to collect in your spectrum image. And if you have other detectors, for example, an EDS detector, or if you have a CL holder, you can simultaneously collect those signals with your seeded patterns at each pixel position. You set up your step size, the number of pixels of the 2D array that you want to scan on the sample, and the pixel step size, and the exposure time. And then you click capture. Then we will take care of everything for you. And what happens is that the camera, here the example is the one view, takes a diffraction image and sends it to digital micrograph computer. And at the same time, other signals, for example, if you have a STEM detector inserted, and as I said, an EDS signal, those will also be sent to the digital micrograph computer. After the diffraction image is captured, camera sends a signal through the STEMx box to the DigiScan box. And DigiScan is the device that we use to control and drive the scanning probe. DigiScan tells the microscope to move to the next pixel position, and then this repeats until the whole area is scanned and your four-dimensional data cube is collected. Once you're done collecting the data, right there within digital micrograph, we have tools for you to analyze the data, and this includes virtual imaging, strain mapping, and differential phase contrast imaging. Okay, so this is actually a nice, flow into what I want to tell you next. Conventionally and traditionally, what people would do to collect for these STEM data sets is that they have several computers that one controls the camera, one controls the microscope. One is to acquire the data set. They need to control different equipment on different systems, on different computers to collect the data set. And then once they have collected the data set, they need to maybe convert it to a different data format, take it to a different computer on a different software interface, analyze the data, and then after spending so much time and effort, maybe they learn that they need to change some parameters for data acquisition on the microscope. So you will have to go back to the microscope, recollect the data set, and then at the end you get the data that you want, and you go to process it and then publish it. With Gatan solution, everything is incorporated into a single software interface. So setting up the microscope and data acquisition, optimizing the data acquisition parameters, data acquisition, and then data analysis and processing is all done within digital micrograph. You don't need to convert the data to a different data format. You can be at the microscope right after data acquisition is done, process your data, and then go back and optimize data acquisition parameters if needed. This is really nice because it makes it simple. It makes it quick and fast to get to results. And it's good for both people who don't have a lot of experience because we have easy to use software interface and workflows, but it's also because it's run within digital micrograph, it means that you have access to digital micrograph and Python scripting, which allows you to modify the experiment and write scripts that will do specifically what you need to do for either controlling the microscope and data acquisition, or once you have the data to do data processing. Okay, so let's get into some examples of what can be done with data once data is acquired. The first and I would say most common and maybe the simplest method is to do virtual imaging. And what that is basically, as I said, you collect your 4D data set. Once you have your four-dimensional data cube, you have access to all the angular ranges in your diffraction images pixel by pixel. So you can use that, and you can use the software then to design your virtual apertures. So in the middle pane here, I'm showing virtual selected area apertures. So on the real space domain, you can draw any shape or form of your selected area aperture. And then what the software does is it goes and sums all the diffraction images in your defined area and gives you a virtual selected area diffraction pattern. You can do exactly the same thing on the diffraction domain, and in that case, you would be designing and defining areas for a virtual objective aperture, and we do the same thing in the software. For example, let's say for these red selected reflections, what the software does is at each pixel position, it goes to the diffraction image corresponding to that pixel, and it sums the intensities in those reflections and then gives you the intensity for that pixel to generate your virtual dark field image. So, right, this is virtual dark field, bright field images or virtual selected area diffraction imaging. Here is an example. I will show this to you during the demo as well. This is a copper specimen at the grain boundary. I have extracted diffraction images from each of the grains, and then we use the reflections, specific reflections in each of the diffraction images to generate the dark field images, and then you can, color those virtual dark field images and get a color map of this grain boundary in the copper sample. Here is a nice example from the K3IS camera from Northwestern University, again using virtual imaging. They are looking at teeth enamel. This is a very beam sensitive sample with the K3IS because they can do electron counting. They were able to do 4D STEM at much lower doses than they used to before. So, and what that gave them was twofold. One, being able to prevent the specimen from damaging by going to lower doses. And because the dose was low enough, they didn't even need to freeze the sample and go to cryo conditions to image the specimen. So before K3IS, because they couldn't do electron counting, they had to go to high doses, and that required to have a cryo specimen to prevent beam damage. And then the other advantage of using the K3IS for this data acquisition was the high speed that the camera gave them, which meant they could collect more diffraction images in a shorter amount of time, which in the 4D STEM case means they could scan a larger area of the sample and collect a larger field of view to get better statistical, information of what is happening in multiple grains in their sample. Right. You can take this one step further, actually. So as I was showing on the copper sample, the example of color coding grains based on their orientation, you can do that to generate an orientation map of the specimen. So again, you collect a 4D STEM data set, then you classify your diffraction images based on the orientation, and then you go pixel by pixel and put that pixel into the bucket corresponding to whatever crystalline orientation it is at, and then you get the color orientation map. This is, I should mention that this type of analysis we don't have implemented in digital micrograph currently. So if you wanted to do orientation mapping, you would have to use, let's say, a Python script or your own home written script to do that. But it is, as I said, an expansion of virtual imaging and classifying the grains. Okay, let me see. I saw a question because it's a quick question. Someone is asking if we can select multiple diffraction spots with virtual apertures. Yes, we can do that. That was shown in the image that I had on the slide, and we will show that to you during the demo as well. Okay, so the next next type of analysis is nanobeam diffraction strain mapping. Here I'm showing an example of a semiconductor device because it's one of the most common areas where semiconductor industry and semiconductor companies would like to measure the strain at the gates, because that's how they engineer the properties at those regions. So the way nanobeam diffraction and with 4D STEM strain mapping works is you collect your data, of course. Once you have your 4D STEM data set, in the software, you specify a region of the sample that does not have any strain. So that is shown here on this diffraction image. So I have specified this region in silicon closer to substrate as an unstrained area. The software is going to calculate a reference diffraction pattern using the diffraction images in these pixels. Then you specify the crystalline direction for which you want to calculate the strain, and then the software goes and pixel by pixel compares the diffraction pattern in each pixel to this reference diffraction image and measures how much the distance between the reflections has changed. The distance between reflections corresponds inversely to the distance between crystalline planes. And if the distance between crystalline planes is different, that means that there is some strain, and that's how we measure the strain. So by measuring the change in the distance between the reflections, we calculate the strain, and we give you the strain in your sample. I like this example because this is one of the first publications out there using K2IF, actually, a long time ago, and the STEMx to collect 4D STEM data set and do nanobeam diffraction strain mapping. As you can see, the high speed of the camera, they were running the camera at 400 frames per second, which is relatively slow to if you think about today's standards and how fast we can go with cameras today. But this was quite fast at the time. They were able to record a 4D STEM dataset from a quite large field of view and then calculate the strain, and as you can see, get this nice statistical information throughout many layers in the sample here, as you can see. Being able to collect 4D STEM datasets fast with the high-speed cameras means that now instead of spending maybe hours or several minutes, 15, 10, 20 minutes, to collect your 4D STEM data, you are collecting data within a couple of minutes, 1-2 minutes, and in a lot of cases within like 20 seconds, 30 seconds. And that means you can add another dimension to your experiment, and here it's showing adding the dimension of time. So running an in situ 4D STEM experiment. So here you can see a doggone-shaped tensile sample in the microscope. What they were doing is pulling on the sample, stopping and collecting your 4D STEM data as they were doing that. So you can do this only if you have a high-speed data acquisition capability so that each data set is not taking too much of a time. All right, another example, I think this is also a nice paper, is talking about strain mapping, not just on crystalline materials, but you can look at the amorphous ring and how the shape of the ring is changing to calculate the strain in your amorphous materials. Again, when we talk about nanobeam diffraction and strain mapping with 4D STEM, most of the time people are thinking about crystalline samples. This is a nice example to show that you're not limited to crystalline sample images. All right, so the next application is differential phase contrast imaging. This is a tool that we have recently added to digital micrographs. It is now available in GMS 3.5, which was recently released. The concept is that if you have a thin specimen and you pass the electron beam through your sample, if there is an electric field, the electric field is going to cause the beam to deflect. And by measuring the amount of deflection of the beam, you can back calculate the electric field in your sample. So here I'm showing an example of high resolution data for the STEM data acquisition. This was actually collected at NSEM using the K3IS at the end of an imaging filter. For DPC imaging, you want to be in large convergence angle conditions, and you are imaging the direct beam, the 000 beam. And what we do is we look at the contrast within the disk, and we measure the move or the shift in the center of the mass of the beam at each pixel position. So that is going to give you the dx and dy maps as you see here. These will be the two components of your beam deflection vector map, as I'm showing here in the color map. And then by calculating the divergence, so this beam deflection is related to the electric field in the sample, and then by calculating the divergence of the beam deflection map, you can also calculate the charge density in your sample. So here is one of the first examples that was published using OneView and K2IS cameras, actually doing exactly the same thing, looking at the at this boundary here and calculating the electric field and also the charge density at the boundary. Yeah, and this is a graphic they got actually a cover of a journal because of this paper. Here is another example, a nice application of differential phase contrast imaging. Frankitite is a naturally occurring material that comes with microscopic rippling, which means that this rippling causes, and how it is, the difference in the rippling and distancing between the ripples affects the electrical properties of this sample. So this customer, what they did is they did differential phase contrast imaging using 4D STEM to see if they could correlate the electric field to these ripples in their sample. They collected a 4D STEM data set. They, as I was explaining before, they looked at the shift in the center of the mass, and then calculated the X and Y components, and looking at the profile of the ripples versus the beam shift, they found a nice correlation between the electric field and the ripples in their sample. Here is another example combining 4D STEM again with in situ biasing. So this example is from Northwestern University using the K3IS camera, looking at the interface of hexagonal boron nitride and moly disulfide here. What they did is they collected 4D STEM data sets without biasing and with biasing the sample, and measured how the electric field at the interface of these two layers changes. Again, you can do this because you can collect high-speed 4D STEM data sets, so you don't have to spend hours or several minutes to collect your 4D STEM data. You collect the data, first data quite fast, within seconds, less than a minute, and then you apply, if it's a bias or if it's a heating experiment or if it's a tensile experiment, you apply your stimulation to the sample, and then you collect the next in situ data point. So virtual imaging, strain mapping, and differential phase contrast imaging are workflows that are currently implemented in digital micrograph. but if there are tools, as I said earlier, if there are tools that we as Gatan do not have already implemented in GEM, you can extend the capabilities by Python scripting in digital micrographs. So you can write your own script, Python scripts, bring them in digital micrographs, and process the data. And one of those examples is the orientation mapping paper that I showed earlier. That is done using Python scripting. Okay, some of the other advantages of using Gatan systems for 4D STEM. As I said, everything is done within digital micrographs. So if you have other equipment like EDS, or if you have a yield spectrometer, you can collect data sets, complementary data sets, within the same software interface during the same microscope session on the exact same area of the sample. You cannot collect yield spectra and 4D STEM simultaneously because usually the detector that is collected, the pixelator detector that is used to collect the 4D STEM data is either pre-GIF or post-GIF. And if it's pre-GIF, if you insert it to collect the diffraction images, it's going to block the yield signal getting to the end of the spectrometer. And if you're doing 4D STEM on the end of the GIF, you're in SM mode and not in yield mode. So for 4D STEM and yield, you have to do them one after the other. But EDS signal, of course, as I showed in one of my first slides, can be collected simultaneously with a 4D STEM data acquisition or as you're collecting your yield spectrum. So here are two examples. The one on the left, we were looking at the sample and we were not sure about the crystalline structure of the material, and we collected some 4D STEM data to make sense of what we see in the yield spectra. And the one on the right is looking at the strain at the interface here in the sample. And by looking at the yield spectra and looking at the valence state of the material at the interface, we could explain why the strain is changing there. Another advantage, as I mentioned earlier, is with Gatan is that you can do filtered 4D STEM. And here is an example of two diffraction images. The one on the left is unfiltered and the one on the right is zero loss filtered. And as you can see, all the haze in the background from the inelastically scattered electrons is removed in the diffraction image here on the right. And that is going to improve the signal to noise ratio in the diffraction images in the 4D STEM data set. That is going to improve the quality of the data of your 4D STEM. And lastly, but of course not the least, is this is also one of the most important advantages, is that you can do electron counted diffraction imaging with Gatan cameras. So here is showing the difference between diffraction images collected on a 1VU camera, which is a scintillator charge accumulating detector, versus a K3IS camera, which is a direct detection electron counting camera. Exact same conditions on the sample, exact same microscope conditions and exposure. You can see the difference in the signal to noise ratio between the two detectors. And then, right, so this is what I wanted to talk about on 4D STEM and STEMx. I see there is one question. So someone is asking if the nanoscale strain mapping is done using nanomechanical testing holders, and what is the size range for these tensile samples. I'm going to have to refer you to that paper. I can put the reference in the chat box, or we can send it to you later. I unfortunately don't know the details of which holders was used in that paper, but I would assume, yes, it's an in situ. It's either a regular bulk holder, tensile holder, or it could be a MEMS device applying strain on the sample. Okay, so this was the first part of my presentation. As I said, with the STEMx box, you can do hardware synchronized 4D STEM data acquisitions with any of Gatan detectors pre or post GIF. And I also mentioned that we recently introduced a Stella camera, which is a hybrid pixel detector. And I want to continue my presentation talking a little bit about this camera because it's a new technology. It's a new type of detector on Gatan's camera portfolio, which is optimized for diffraction imaging. So the Stella camera is the only hybrid pixel detector that is fully incorporated into digital micrograph for diffraction imaging. And let's go into more details. Okay, so what is a hybrid pixel detector? This is a direct detection counting camera, which is composed of a sensor that is bump padded to an ASIC. And so it's direct detection and it's counting. Electron counting and direct detection minimizes the noise. We use a dexterous technology in this camera, which is using instant retriggering. And what that means is that you can do electron counting at much higher dose rates than is common for electron counting cameras like K2 and K3. And then because of on-the-fly digitization, it gives you also the highest dynamic range, which is another very important quality of the detector that is needed for diffraction imaging, because usually what you have is the dark background of the diffraction and then high intensity diffraction reflections. So you need a high dynamic range detector to be able to collect all of that information without saturating your camera. Here is an example showing the dynamic range of the Stella camera. So on the left-hand side, you're looking at a single diffraction image with 0.5 millisecond exposure time. And what I've done is I have drawn a profile line along my direct beam, so the high intensity beam here, and this reflection, the high resolution reflection, all the way on the top here. And you see that profile line in logarithmic scale here on the right hand side. So the yellow box here is showing the intensity from this reflection. You can see it's like 4 or 5 counts, as opposed to several orders of magnitude counts here for the intensity at the direct beam. So this is directly showing you the dynamic range of the camera. I am not saturating the detector at the center beam. At the same time, because I am collecting data in electron counting mode, I am collecting signals from 1 or 2 electrons that results into 4 or 5 counts here in the image. So this is showing you both the advantage of electron counting, high signal to noise ratio diffraction imaging, at the same time, the high dynamic range of the detector. Here is an example of using the high dynamic range of the camera, looking at this material, NCS. What happens is that the chirality in this type of material affects its electronic structure. Unfortunately, it's not very easy to detect or image chirality in bright field imaging. So what you can do instead is go to seabed mode and look at the inversion of the reflections of the diffraction pairs. As you can see here, for example, on the right-hand side, if you look at these two boxes, we have zoomed into those, and if you draw a profile line, you can see the intensity, the diffraction intensity in these pairs of reflections in first order value zone is inverse. And this is showing you the chirality in the sample if the sample is in the right zone axis. And I have also, to show the dynamic range, again drawn a profile line along this dashed yellow line, which is shown here on the right hand side. Again, you can see the intensities in the beam, in the reflections and diffraction spots, and also the central beam shown in the middle. Okay, let me see. I'll get back to that question. I just got another question. Okay, so the other advantage of the stellar detector is its high speed. So we have been talking about using different detectors for 4D STEM imaging. And as I said, we make the hardware synchronization via the STEMx box. The detector is gonna be the timing master for your 4D STEM experiment. So depending on which camera you're using and how fast that camera can operate or collect images, that's how fast you can collect your diffraction images per pixel and how fast you can run your 4D STEM experiment. So with the Stellar camera, you can run the camera at more than 16,000 frames per second. And what that means is that you can run your 4D STEM experiment at more than 16,000 pixels per second. So this is 16,000 STEM pixels, so 16,000 scanning probe positions per second. And what this gives you is that you can, as I was mentioning earlier, collect a larger field of view on your sample in a shorter amount of time. And also, if you have issues with specimen drift or specimen damage, because you're collecting data faster, you can eliminate those problems or at least minimize those problems. And right, so because you can run the camera really fast, as I said, you can collect a large amount of data set in a reasonable amount of time. Here's an example that shows you high throughput 4D STEM data acquisition for differential phase contrast imaging. These are coarse silicon molybdisulfide core shell particles. By changing the properties of the core and designing what kind of shell you put on those core, you can actually engineer the electrical properties of your particles and design different types of material properties. So in this experiment, they were trying to understand how the interface between the particle core and shell is affecting the electric field. So they collected the 4D STEM data and they measured, again, the center of mass shift in digital micrograph on these particles. This is showing just a couple of those particles, but because they were able to do this fast, they actually collected data sets from many of these particles in a short amount of time. And as you can see, they generated this DPC color map showing the electric field in the sample. Okay, one other important point to make about the Stellar camera is that because it uses hybrid pixel detection technology, it is optimized for low kV imaging. So looking at our camera portfolios, Rio and OneView are scintillator-based cameras that are optimized for 80 to 200 or 300 kV regular imaging. K3 is our monolithic direct detection camera that is a STIM sensor where electrons pass through the sensor. And what that means is that it performs better and it gives you higher DQE, higher signal to noise ratio at higher KVs. So it's optimized for 200, 300 kV. And really, we don't recommend you using it below 80 kV. And Stella is on the other side of the spectrum because it's a hybrid pixel detector. You get a smaller point spread function as you go down in an electron beam energy, and that means that you get higher DQE at lower KVs. So it actually complements the K3 capabilities at the lower KV ranges. And this is ideal for all the new types of beam sensitive materials that people are looking at nowadays. These could include battery materials, 2D materials like COFs and MOFs and zeolites, polymers. All of these types of materials have issues with being damaged at higher KVs. And so you can use this camera to do 4D STEM or any kind of diffraction imaging at low KV on these types of materials. Here is an example, again, on moly-disulfide, tychography, data set collected and reconstruction done at 40 kV, again, on this beam-sensitive sample using the Stella camera. And right, so you can, the same thing is with our other detectors. This is fully integrated within digital micrographs. So you can do, you can collect your 4D STEM data set and do all types of data processing as I have been mentioning so far, like virtual imaging, strain mapping, and differential phase contrast imaging in digital micrograph. And with the Stella camera, you are using the electron counting and high dynamic range of the detector, at the same time, the capability to go to low KV. So all of these examples that I have on this slide have been collected at 80 kV or below, which was not easy to do or even possible with other detectors prior to Stella. Okay, so yeah, that's, I think, one of the last slides that I have, right? So with STEMx, you can do 4D STEM data acquisition and data processing, hardware synchronized with pre and post Gatan detectors. And once you have the data sets, you can do data analysis like virtual imaging, differential phase contrast imaging, and strain mapping in DM. We will show all of this to you in our live demo after my presentation. Okay, yeah, so that's the last slide. If you have any other questions, please submit them right now. I think there is one question. How fast does the 4D STEM detector record the image? I think I answered that question. So that depends on which camera you're using for data acquisition. With the OneView camera installed at NC State right now, you can go 4K by 4K, 25 frames per second, which means 25 pixels per second for 4D STEM, and up to 300 frames per second. With the Stella camera, as you saw on the slide, you can run the camera more than 16,000 frames per second, which means you can collect your 4D STEM data set at that speed. So it depends which detector you are using. And we have a wide range of capabilities depending on what type of detector you have installed on your microscope. So right, so they're, yeah, sorry, Jordan. They're asking if the in situ strain mapping data was done as they were pulling on the sample. I don't think so. I think you're right. So they would collect the data before they apply the force, and then they would apply a force, stop, and then collect another data set, and do this in 4 or 5 times to collect the in situ data set. If you do this simultaneously, your sample will be moving and the crystal will be changing. So I don't think that's really possible. Right, Jordan?
Yeah, thanks, Anna. I just wanted to give everyone in person an opportunity. Were there any questions from any folks in the audience today? Yeah, we've got one question.
For the in-situ tensile test, the strain mapping, what's the accuracy for the calculated strain?
Yeah, so the question was on the in situ tensile testing, doing strain analysis. What is the accuracy of that type of analysis?
So 4D STEM nanobeam diffraction strain mapping gives you 0.1% strain accuracy. That's just the accuracy of the technique. And for spatial resolution, that depends on your microscope conditions, of course. But remember, we are running the STEM in close to parallel conditions, nanobeam diffraction. So your STEM probe is going to have a larger diameter as opposed to if you're running at larger convergence angles. So spatial resolution for strain mapping is usually 1 or 2 nanometers.
Any other questions for folks here? I had one question from a colleague. So how would you capture 4D STEM data running in a camera at these hundreds of frames per second or hundreds of pixels per second if the sample drift rate was on the order of like several or maybe even 10 nanometers per minute? Can you comment on that?
How can we do that? Okay, so one, a lot of times because you're collecting the data and you have to put the numbers next to each other to see which one makes more sense, you either collect your data really, really fast before giving the sample to drift, or if that's not possible, we will show that to you in the software interface. We have a drift correction algorithm during 4D STEM data acquisition. So you can actually have the software to stop or pause as it's collecting the data, go to a reference area, measure the drift and bring the sample back, and then continue data acquisition.
Great, thanks.
Yeah.
I don't think there's any questions here on our side, Anna.
I got another question, looks like. Can the STEMx also work with complex beam manipulations with beam precession? Okay, so we STEMx box comes with a DigiScan, and right now we do not do precession diffraction with the DigiScan box. The next question is, does Stella have any option to avoid the exposure or recording of direct beam as a beam stopper? The camera doesn't come with a beam stop, but you can use the microscope beam stop, or if it's at the end of the GIF, you can use the beam stop at the entrance aperture of the GIF. But I can tell you, I haven't found a situation where I needed to use a beam stop with the Stella camera. Okay, I think that was the last question.
Okay, Anna, thank you. I think I can take over then. Hello, everyone. In case you weren't here in the morning, my name is Fernando Castro. I'm an imaging application scientist here for Gatan. Right now, I'm located on the ground floor of the NC State building, driving the microscope here. We have a probe-corrected Titan with a one-view camera, as we've been discussing, along with our STEMx system, running at 300 kV. So I will start this demo by showing you a little bit about how GMS works, specifically with collecting 4D STEM data, as Anna highlighted a little bit in her presentation, and then I will hand it back to Anna to show in depth all the different data processing methods for 4D STEM that are implemented directly into digital micrograph. So if you're here in the morning, we were in TM mode on the microscope. Now we're here in STEM mode. Again, here on the top left of our digital micrograph screen, that's reflected here by being in scanning mode, and it's showing us we're in nanoprobe mode. On the microscope system, again, we have all these nice controls for controlling the column valves, beam blanking, opening and closing the Foster screen, inserting the camera. So we'll get started with that, right? So we can very easily open the column valve. We see again here, the microscope diagram is updated, We can then unblank the beam, which I'll do now. And well, I'll wait for that actually. And once we're ready to start imaging, again, we go to the technique manager here. In the morning, we went to STEM imaging to collect, or sorry, TEM imaging to collect our TM images and look at some in situ capabilities. Now, because we're interested in 4D STEM, we'll go to the STEM SI technique here under analytical TEM. So SI, if you're not familiar with the terminology in Gatan world, stands for spectrum imaging. So it's the technique we'll use for collecting line scans or multi-point profiles or maps, as you can see here, either for EDS, EELS, or 4D STEM. In this case, we're just focusing on 4D STEM. So once we go to the STEM SI technique manager, we get our options to scan. This is the controlling the scanning and viewing of the STEM detectors on the microscope. We'll see this controls for setting up our 4D STEM experiment using the STEMx system. And then again, we have our one view camera controls, which we will be using for actually collecting all of the diffraction patterns, as Anna was explaining in her workflow. So I'll unblank the beam and start viewing. We're still working with the same sample here. It's our BTO sample. You might notice we have a little bit of contamination building up in certain areas, but because it's a probe corrected microscope, we should be able to zoom right in and start seeing some nice lattice structure. So I'll just move the area over to a new area, a little further away from all this contamination. And the great folks here at NC State have helped us get everything going, and we can see a nice lattice structure. Obviously, so I'm going to blank the beam just for now, just because while I explain things, we are getting some contamination on the sample. But you can also see when I'm chatting, because I'm about 1 foot away from the microscope, and it's a very sensitive atomic resolution microscope, I introduce some vibrations into the system here. But anyway, here's our image. So I will, from the scan palette here, there's a lot of different things that we can do. It's very similar, you'll notice, to the one view camera options here on the bottom. So one of the things that we can do, I'll just pause that and blank the beam so we have an image here. So there's different modes we can be in. We can be in spot mode or not. If we're in spot mode, when we pause the beam, we'll see here that there's a place to park the beam on the image, away from our sample. We can do things like rotate the STEM image if I choose to activate it, so you get the proper orientation. In this case, it doesn't really matter because we're not looking at a specific interface or anything like that. Something else that's super nice is that we can use a focus loop here. If I click this, for example, I can see here, there's a sub area that comes up, and I can use the arrow keys actually on the microscope to increase the pixel time or the pixel resolution to really help me focus the sample. Right now I was already pretty much in focus, but that's something that's really nice that comes within digital micrograph. And as you can see, we're already building a little bit of contamination, actually a lot of contamination. So I will just keep blanking this while I keep discussing. So those are the main options. Here, obviously, we can choose our pixel time, and there's options here for being within search mode or in preview mode that you can set up differently to have different pixel times, different STEM image resolutions as you see fit. So the search will be a little faster. I'll unblank the beam again. We can still see the lattice structure. Maybe we have a lot of contamination, but that's okay for this case. We can still see that we have nice atomic resolution of this BTO sample in this clean area here. So when we're ready to take an image, I'll just click capture. And I'll just blank the beam while I do that. So here's the image we captured. We can see a nice resolution. Obviously, there's some drift. We're getting contamination. I'm talking. So it isn't the most amazing photo, but it still shows off the the capabilities of the microscope in a not an amazing case. So if we want to start collecting our spectrum image, our STEM map, we select the option here we have for the signals. In this case, we select seabed just because we have only the one view camera currently working through digital micrograph here on the microscope. But as Anna mentioned in her presentation, if you had, for example, EDS detectors that were connected up to digital micrograph and to the camera, you could collect your 4D STEM data at the same time that you collect EBSD data in a map or a line scan or something like that. So because we want to do mapping, we'll go to 2D array. And then we get all these options here. Notably on this, in the main viewing window, we have a spectrum image showing up, a little box. This box is what's going to define the region of the image that we're going to use for collecting our map from. Right now, again, I still have the beam blank, but we'll get to this later while I explain everything else that's going on in this palette. So we can, of course, choose our pixel time, the number of passes that we want to make for the map, and then the size of the spectrum image in number of pixels, and then that, based on how big we make the box or how many pixels there are, that is what's telling us our step size. But you can also put in another step size, and the software will program everything out. For example, right, if we can increase it, we can see that the step size here in angstroms is changing or increasing. And something else that I want to point out here is on this left-hand side, as you are setting up everything to go for this experiment, this is updating live also to show you how long it'll take you to acquire your map and how big the data set will be that we are going to collect. So if I had a very small step size, for example, we can see that even though I haven't changed the pixel time, well, that we have a little more pixels, but over this large of an area, we're very dramatically increased the size of the data set that we'll be collecting with 4D STEM. So we'll keep that to a minimum. I think we had something like a 1 angstrom step size, which is okay. And that gives us something much more manageable, right? We'll collect each pass will take about 1.5 minutes. The data set we collect will be only 72 gigabytes, which is much more workable than 172 gigabytes. So the other thing we want to set up here is the one view camera. So with the one view camera, as Anna was saying, in the whole signal flow process, you can collect your 4D STEM data set as fast as your camera can essentially capture the diffraction pattern. So earlier in the morning, we were always doing 4K by 4K imaging because at 25 frames per second, that's like more than enough to collect a really nice in situ video, or if we're just navigating around on the sample with the camera. Now we want to go way faster, right? Because if we were doing 4K by 4K imaging, we have 25 frames per second, so we'd only be going 25 pixels per second, and that might be too slow in many cases, especially based if you have a big spectrum image in number of pixels that you're trying to collect. So if we bin down the image to 1K by 1K, our max frame rate at this binning is 200 frames per second, which is an exposure time of 0.0005 seconds. So because the camera's the timing master, it's essentially the rate limiting step in the signal flow, this binning down the image is a good idea, enabled to go faster. The only thing you have to make sure also is because many times we're looking at the center transmitted beam and you're looking at subtle changes in contrast or something in the diffraction features, you just want to make sure that this image is high enough resolution to capture those features in the diffraction pattern. So that's the trade-off when you're thinking about things, especially with a camera like the one view camera. Obviously with the Stella camera, you can go way faster, so it's less of a concern. But one of the things I think we checked is we'll make this 128 by 128. So essentially everything is set up. One thing I'll, right, and at the very end, I'll open up the image and show you how everything is done, so we don't build up too much carbon contamination. The other thing I'd like to show you is the preferences here for the STEM SI acquisition. So one of the questions was drift. What can we do to correct for drift? And if we go to the setup and we click this drift tab, there's actually many different ways that we can try doing drift correction. Essentially, if we enable it, we'll have a little box that pops up similar to with the imaging mode to track a feature and do the drift correction, but we can the software can start applying drift correction after every row, for example, every certain amount of seconds, every certain amount of pixels, or every certain amount of frames or passes. So that's you have a lot of flexibility about what you can or how you can correct the drift in your scanning spectrum image. But as Anna mentioned before, if you have a really fast camera, a lot of times you can just collect your 4D STEM data set super fast with these high-speed cameras and not really even have to worry about doing the drift correction. The other thing too is in addition to doing binning on the camera, we can also use binning in the software to reduce the image size and of the one view camera image if we so choose. Okay, so now everything essentially is set up. I'll show you how we can get going. So here's our spectrum image. Say we want to look at like this size, right? We're not really doing atomic resolution stuff. I'll zoom it a little more and maybe move the sample further away from the area where we were at. Something like here. And then the other thing I actually haven't showed you is what it looks like on the camera, right? So if I stop viewing and I'm in probe mode and I have to insert the camera here, which takes a few seconds. So I'm just blanking the beam while the camera inserts to minimize the carbon contamination on the sample. But we'll see here now what popped up here on the right side is the camera image from the one view. So if we raise the screen, it's raising. We should be able to see a diffraction. Oh, sorry, I have the beam blanked. So why can't I see anything? Pattern. But this is the probe that we are seeing here on the one view camera. One thing that I'll mention here also that I haven't mentioned is I'm using a longer camera length than you might be familiar with using, just so that we take up and we're making use out of making the most use out of the sensor as possible. So I had changed this binning here to 4K by 4K just while testing. So I will go back to 1K. Right, and here's our 4D STEM data set. So let me just go back. So we'll start viewing again.
Do you have the detector inserted?
Yeah, I took out the detectors. Now I have to insert it. Thank you, Anna, for reminding me. So as you see, we're kind of dealing with a lot of contamination here. But here's our
someone is asking what is the contamination. It's basically carbon contamination on the sample. So it's the sample is not super clean, or the vacuum. That's where it's coming from.
Yeah, that's right. So one of the things right now we have the STEM detectors in actually. So if I start viewing the sample here, and we look at the camera now, the image, we can see that actually the STEM detector is partially blocking the beam. So what we can do, for example, is just capture our image. That will, sorry, I'm being a little quiet here just so it acquires, okay? So we can capture our image here. Now within the thermo software, I'm retracting the detector. And now if we view our camera image, it's not blocking the probe anymore. Or sorry, it's not, the detector isn't blocking, the diffraction pattern. And now we can clip capture. Everything should be set up. Well, I'll just go through once more, make sure everything's set up. It wants to use this image for some reason.
Just do a preview maybe. And then you can drag the spectrum image box to that preview image.
Yeah. So this is our box here. Should be okay. It's still working here, so I'll just work with this one. And I'll minimize this so it's not confusing. So here we are. And essentially, once everything is set up with the spectrum image and with the cameras we've already discussed, we just click capture. So as it's capturing here, yeah, I didn't take out the detector.
Fernando,
Yeah.
I think, and also you didn't change the pixel dwell time. So when he switched to 4K by 4K, the software automatically changed the exposure time to the allowed exposure time for 4K mode. But now that we are using 1K, we can go faster.
Yes, thank you for catching that, Anna, because I missed it.
Yeah, no problem.
So I'll just reset the pixel time here.
Right,
This
and you
is our
can see
image here.
instead of 10 minutes, we can do 1.5 minutes now.
Mm-hmm. Now I'll capture.
Right. Oh, I think STEM detector is in.
Yeah, I'll take it out
now. Yeah. So as I was saying in my presentation, and I showed in the video, one of the first few slides, when you're collecting 4D STEM data, for setup, you do need a STEM detector so that you can find the region of interest, focus, and navigate. But once you have selected your data acquisition area, you can take out that detector, as Fernando is doing here, so that you are actually not blocking off the camera by your STEM detector aperture, and are collecting the full angular range of your diffraction images in each pixel position. Whatever, we'll show that to you when I switch to show you data processing. Whatever kind of annular virtual diffraction, annular image, or any virtual bright field, dark field image that you want, you can reconstruct after data acquisition is done.
So as we were seeing here, we were collecting the diffraction SI, also our dark field image, because we took out the detector after just a few rows. That's why we have this sort of darkness. There was no signal hitting those dark field detectors. We were also seeing the probe image, the diffraction pattern here on the right, and we can see within our survey image here, the spectrum image had that yellow line going down showing you the scan. So once that's all collected, it comes up here. Oh, sorry, it's just this. So we can interact with this data set immediately after we capture it. So if I'm right clicking to access these tools, and within the spectrum imaging paradigm, we have the tool called the SI picker tool. So we can take this picker tool to select a single pixel. As we see here, I've selected a single pixel once I zoom in, and then we see the diffraction pattern. So we can take this pixel, drag it around different parts of the spectrum image map, and see changes in the diffraction pattern down here. We can do things like make the area of interest larger. You just have to be careful about making it too big, because then it has to sum up all of the different frames here. But for example, you can see as I scan across the image, how the diffraction pattern changes. Something else that's super nice is you might be thinking, okay, well, where does this correlate to on my sample? Because this diffraction SI doesn't really have interpretable contrast. You can just take this picker tool, drag it to another image, and leave it there, and then it gets linked up. So as I move the diffraction SI here, not only can we see the probe diffraction pattern change here on the bottom, but you also see the spectrum, the position on the spectrum image moving around. So if I zoom in here a little bit, and if I drag it either through the survey image or the SI image, the diffraction SI image, everything is linked up together, which is super nice. So you always sort of know where in your sample you're looking at when you're doing a certain, looking for a certain feature or anything like that. This is true for both 4D STEM, but also EDS EELs, any type of information that you collect through the spectrum imaging workflow in digital micrograph. So this is 4D STEM acquisition. Now I think I will hand it over back to Anna so she can show you about data processing.
Thank you, Fernando. Can everyone see my screen? Should be seeing digital micrograph. Okay, perfect. So that was data acquisition. You saw that it's quite simple. You go to STEM mode on your microscope. You find the region of interest. You make sure you're focused. You set up the proper camera length and diffraction imaging conditions on the camera. You select the camera mode that you want depending on what kind of pixel resolution you need on the camera and how fast you want to run the camera. And then using the STEMSI palette, you go and collect your data. Once you have collected the data, all the data analysis tools are also within digital micrograph. And Fernando started showing you some of the tools, and I'll expand on that here on my computer. Before we get to that, there are a couple other questions. So one is, Fernando, do you know what's the convergence angle you were using?
Yeah, the convergence angle right now is 19 milliradians.
19 milliradians. And I don't think you're in FM mode, correct?
No, I'm not in FM mode.
Yeah, it's not. Yeah, and then the other question is, are you able to rebuild the atomic resolution HADF image from the 4D STEM data? If the sample is not drifting as it was when we were collecting the data set, then yes, you should be able to reconstruct the HADF image from your 4D STEM data. As Fernando was collecting the data, I was speaking, and I think the sample was drifting quite a lot as well. So the data set that we just collected, I don't think we were able to do that, but if you carefully collect the data fast enough, without contamination, you should be able to reconstruct that image, yes. And I'll show you an example here in one of the examples that I want to talk about. Okay, so I'll start the data processing part, and then I'll get back to questions after that. Okay, so here is the first example. I want to show you how we do virtual imaging with 4D STEM datasets in digital micrograph. This is the same grain boundary, copper grain boundary sample that I showed in my slides. As you saw on Fernando's demonstration part, you right-click on the image and you access this SI picker tool to extract diffraction images from individual pixels. So if I put this picker tool on my any of the pixels in my data set, I can extract the diffraction image from that specific pixel. And you can see as I move to different grains on this grain boundary, the diffraction image is changing. This is as if I have a selected area electron diffraction aperture inserted on this specific pixel on this specific area of the sample and getting a diffraction image from that. So if I increase the number of selected pixels by the picker tool, then software is going to sum up those diffraction images and give me the selected area, virtual selected area diffraction image from, again, that selected area of the sample. This data set was collected using the 1D camera. So now I can go on to my diffraction domain and do the same thing, apply a virtual objective aperture and reconstruct the virtual bright field, dark field images. One way to do that is if I click on my diffraction pattern and I click here on show range, you can see this slice toolbox appears. And this is my virtual objective aperture now. If I move it around on different reflections, you can see the contrast in my the display of my 4D STEM image is changing. That depends on which reflection I am selecting or on my diffraction image. And this is how you reconstruct dark field, bright field virtual images. This is one way, of course. You can also click on your diffraction image and select any shape of an ROI. Let's say I select an oval and draw it on your diffraction image. And this can be either one ROI or multiple ROIs. Then you go up here to the SI tools and you say map signal or signal dynamic. And this is basically if you want to calculate here, because I've selected the direct beam, the virtual bright field image, or if I want to move my region of interest on the sample, as I was doing with the slice tool, to calculate the signal dynamically. So this is my virtual bright field image reconstructed here. We can also, as I was saying, reconstruct annular detector virtual images. So if I select this bandpass here, the mask, and I put it on my diffraction image, I can select the inner and outer diameter or angular ranges for my detector here by moving the inner and outer diameters of the mask. And then I go do the same thing, go to SI, map signal, and this is going to be my annular, virtual annular detector signal here. So what the software does, it goes into the 4D STEM data, pixel by pixel. It sums up all the signals selected by this range that I specified, and then put that number in the pixels here to calculate the virtual image. So this is different ways of reconstructing virtual bright field, dark field images or selected area diffraction images from your 4D STEM data set. A couple of other tools that we have under the SI menu is this nice Align SI by peak tool. If you have done spectroscopy, this is similar to what we do with yield spectra Align SI by zero loss peak. Basically, if you are collecting a data set on a microscope at low magnification in STEM mode, sometimes because the scanning cores are imperfect, you will see that the central beam in the diffraction pattern moves. And in order to correct for that movement, you can select your central beam using an ROI. So I draw an ROI box on my central beam, and then I go up here and I say Align SI by peak, and then it goes and pixel by pixel measures the shift in this diffraction spot, and then corrects the 4D STEM data or moves the diffraction to the center pixel by pixel. The other tools that we have here are, if I select my 4D STEM data again, is rebinning tools. I don't see it. And extraction tools. Hold on. Oh, sorry, it's under volume. It's not under. I'm sorry, I'm confusing myself. So, as you saw, 4D STEM data sets can be quite large depending on how many pixels you scan and how large of an image you collect on your diffraction camera. So we recommend that you bin your data and reduce your data size as upstream as possible. So if you can bin the data as in the software or using binning on the camera hardware as you're acquiring the data, that is the preferred way. But sometimes we just don't do that, and we get a quite large data set that we cannot handle or easily handle. And in order to reduce the data under this volume tool, we have several options for you. You can rebin any of the 4 dimensions of the image, so the diffraction dimension or the spatial domain dimension. You can also, if you go back to the volume tool, you can extract a volume, a smaller volume from your large volume. So again, you can cut this volume in all the 4 dimensions. The first 2 are real space, and the second 2 are the diffraction image dimensions. And you can also, I didn't want to do that. And you can also do a subsampling. Usually you want to do this on the real space dimension. So this is as if you reduce your spatial resolution and skip pixels in your real space image. So these are several ways that you can post-process and reduce the data after data acquisition is done. Let me see if we have questions about this one. Okay, I don't see any questions about data processing coming in. So I'm going to move to the next example data set, and this one is to demonstrate how we do strain mapping in DM. So I have a data set here open that is from a silicon germanium multilayer, and as we go down in these layers, the content of germanium increases, and by that we expect to see more strain in the silicon lattice. So as I go down into these silicon germanium layers, I should see more strain measured. If I, again, right-click on the image and extract a diffraction image from this data set, this is collected on a K2IS camera. I am going to move the picker tool up and down the lattice, between the lattice and the silicon, and you can see it kind of breathes. So you can see the diffraction spots going in and out, and that's exactly what we are measuring when we are measuring strain. The change in the spacing between the diffraction reflections is related to the spacing between crystalline planes, which gives us the strain. How much has it changed compared to bare silicon? Okay, so for strain mapping, what we do is we go here on the right-hand side to data analysis technique and select 4D STEM. And you can see we have strain mapping here. And what you want to do is simply start from the top of the window and make your way down. The first step to specify a region of the sample that is not strained to calculate the reference diffraction image. To do that, again, I right-click on my image and I select this U tool, on strain area tool, and I draw this green box on my silicon layer, and then I go to my strain mapping technique palette and click on calculate reference from data. So software automatically calculates a diffraction image that will be used as a reference to measure the strain. In this diffraction image, you specify the central beam. You want to change the size of the selections by changing the size of these red circles to contain the diffraction spot and also some tails from this center beam, because this is what the software is going to use to calculate a template to find the rest of your reflections. And then U and V are going to be the directions, the vectors for which we are planning to calculate the strain. So depending on your crystal orientation, which zone axis you are at, you select those two vectors and put them on the corresponding reflections. And then this green circle tells the software how many orders of the reflections, diffraction reflections, I want to include in my calculation. If you include more reflections that have high enough signal to noise ratio, you're going to improve the accuracy of your calculations. But if you include, like if I make it this big and include those low signals, there is no point, because I'm introducing more error and also more computation time for my strain mapping. So I'm going to make it to contain just this first order reflections for now. Now I'm ready to move to the next step. Oh, one more thing to mention here, you can see we have a drop-down option for a reference diffraction image to use. This drop-down allows you to use a different diffraction image as a reference, something that has been calculated from a different data set, but a data set that has been collected with exact same acquisition parameters. So you want the same convergence angle, the same camera length, the same camera parameters, but in a lot of cases, in a region of the sample that you are trying to calculate the strain, you do not have access to an unstrained area. So this is the solution for that. You can have a standard sample that you don't expect to have any strain in. You collect a 4D STEM data set from that unstrained sample. You calculate the reference image from that data set, and then use that to apply and measure the strain in your other data set. Okay, so once you have selected the reference diffraction image, we can calculate the disk template. I just click on disk, and it is now calculating the disk template using all the diffraction images in your 4D STEM data set from the central beam selected area that I have defined here by the red circle. And I am now ready to move to the next step, which is first, I can define a diffraction pattern rotation angle. And this is because in many cases, as it is here, there is a rotation angle between the diffraction image and the real space scanning dimensions. And if you want to, and the software calculates the strain in X and Y directions of the diffraction image. So if you wanted to make an easier sense of what is what, you can have the software, when it calculates the X and Y direction diffraction strain, rotate those vectors and give you the correct numbers in the directions for your real space image. So for here, I have a negative 25 degrees rotation. So I go here in the setup box and I enter that negative 25 degrees for the software to use. And the way you measure this is when you are in the diffraction image, you defocus the beam and you get a shadow image of your sample. And from that shadow image compared to your STEM image, you can calculate and measure how much rotation you have. Okay, I have everything set up now. I'm ready to calculate my strain mass. One last thing, if you want to do a quick strain mapping and you don't want to run it on a full data set, here you can apply some sampling interval to the real space dimensions. So I can skip, let's say, 2-3 pixels and do that quickly. But right now I want to calculate it on my whole data set. So I put in 1 and I click calculate. So now it is going pixel by pixel in my 4D STEM data, comparing the diffraction images to this reference diffraction image and calculating the strain based on the difference in the spacing between the reflections. This is the direction for which I expect to have strain as I go down the layers. I can go here and change the contrast so that we can better see, and I can actually make it color. So you can see as I go down, I can also add add an intensity bar here for you. So you can see as we go down the layers, the amount of strain is increasing as the amount of germanium is increasing in the sample. The next mask, this one is the strain in the Y direction. We don't expect to have much. You can see as I scroll down, if you look at the value shown here at the bottom left of the frame, you can see it's less than 0.1%. So this is within the error margin. And if I look on here, it's 1.5%, 1.6%, and 1.72% here in the bottom part. Okay. This is what I wanted to show you for for strain mapping. Now I'm going to switch to the next example, which is differential phase contrast imaging example. Okay, so one question was, can you reconstruct atomic resolution STEM image from your 4D STEM data? Here is an example showing exactly that. So if I select my picker tool, I put it on this this data set. This was actually done using the K3IS camera at the end of a filter. So this is a filtered 4D STEM data on a counting detector. For DTC, as we said, you go to large convergence angle. You can, because you are in large convergence angle, your probe size is quite small, so you can do atomic resolution imaging in most cases for electric field measurements. And you are looking at the direct beam, and what we want to do is we want to measure the shift in the center of mass of the beam as we go across atomic columns. And you can see as I move my picker tool, the contrast within my beam is changing, and that's exactly what we want to measure for the DPC signal. And if I again click here on my diffraction image and select show range, this is the slice tool or the virtual objective aperture, and you can see by moving this around, I can change the contrast in my display for my 4D STEM image, and that this is how you reconstruct different types of bright field, dark field images from your 4D STEM data. So you don't need to have the detector inserted as you're collecting your data set. All right, so let's go to differential phase contrast imaging. In order to do that, we again are in the 4D STEM analysis technique, and we use the DPC panel. There are a couple of ways that we have implemented where you can calculate the differential phase signal. The first method is similar to conventional method of differential phase contrast imaging, where people used to have segmented detectors, segmented annular detectors installed in their microscopes, and they would calculate, or they will measure the difference between opposing segments to measure how much the beam is moving in each direction. So, and that is done using the center part of the DTC panel. You can see I can create a mask with as many annuli and sectors as I want. And then you can name that mask and then have it in this drop-down menu. I have already designed the 4 segments mask. So now I'm going to click on show and show it on my diffraction image. And for this mask, you can modify the angular range selection for as many sectors as you have defined. And you can also move around your sector selections, the directions, or the angular ranges in the diagonal range for each of the sectors that you have in this virtual segmented detector. Now, once you have defined the areas you can, if you right-click on the image and go to the DTC menu, you can go to Configure Mask and then define signals for this specific virtual detector that you want. So as I said, the difference between the opposing sectors is going to tell us how much the beam is moving in those directions. So I have G minus E and H minus F. If I wanted to, I could also calculate any other formula and calculate any other signal that I want. For example, I have a bright field signal defined here, which is the sum of all the sectors here in the central circle. You can add more signals and you can delete what you had before, etc., etc. So once you're ready and you have defined your signals, you can go ahead and simply click on Calculate. And it's telling me that you made some changes. Do you want to save them before you calculate the signals? I don't want to. I want to use the previous selection that I had saved before. Now it's asking me, so the software is automatically going to find the center of the mass of all data sets, diffraction images, and then put the virtual segmented detector centered to that center of mass to calculate the signals. So it's telling me to give it a cutoff radius to do so. So what it has selected automatically looks fine to me. So I'm going to click OK. And now it found that center automatically. It put the segmented detector on there, and now it's calculating the signals as I had defined. So the first one is G minus E, so it's going to measure the beam shift in this direction. And the next one is H minus F, so it's going to measure the beam shift in this direction. And then the last one is a bright field, which is the sum of all these four sectors here. So this is the first method to calculate this DCC signals, as I said, similar to the conventional having actual physical detectors installed in the microscope. The nice thing here is, unlike on the microscope where you select your camera length and then you're stuck with it, whatever amount of signal that lands on your segment depends on your camera length. And once you have selected it and you collected your data, you're done. Here, you can, of course, go into the software and change these angular range selections and modify your signals and improve the calculations in the software after the fact. Okay, so the next method to do DCC measurement is using the full diffraction signal, not just the edges and what lands onto our segmented detector sectors. And for that, we have this beam displacement section on up on top. You can either use a center mass calculation, or you can do cross correlation. So this is where I think most of the times when people want to calculate magnetic fields as opposed to electric fields, and you are more interested in the full shift of the disk as opposed to the shift in the contrast within your disk, which is used for electric field measurements. For this example, I'm going to use center of mass. And here, the same as for strain mapping, if you have measured the diffraction rotation, you can apply the diffraction rotation angle here if you know what it is. You bring your 4D STEM data to the center, to the front of the image, and then you simply click measure beam displacement for me. It's going to the diffraction images pixel by pixel, and it's calculating the center of mass in the diffraction image, comparing it to a reference center of mass, and calculating how much it is different to that reference. So the same the X and Y directions are the diffraction X and Y dimensions. So if you know there is a rotation angle between your diffraction dimension and your STEM or real space dimensions, you can apply that in the software and have it automatically applied when it outputs the X and Y directions. So I'm going to let this finish. once we have these two components, these are the two components that we are going to use to calculate the beam displacement vector map. That's the color map that you saw on my DPC slides earlier. Right, so now that I have these two components, it is the same as having these two components from my virtual segmented detector. I'm gonna use these two and go to the bottom right here and click on calculate vector displacement. And it is asking me to tell it which two images I want to use as the two components for my vector map, dx and dy, m and u images in dm. And I click OK, and it automatically calculates the vector map for me. So this is a vector image. If I scroll on the image, you can see at the bottom left here in the ribbon, the modulus shows the magnitude of my vector, beam displacement vector, and which is in milliradians from the diffraction images, and and also you can see the angle. And the angle corresponds, as you can see here, from the color wheel, the direction of the beam displacement vector map. So these are the atomic columns, and you can see the beam. So, for example, here with this this purplish color, which we have there, it means that the beam displaced in that direction, which is opposite to the electric field direction. And as I said, from this beam displacement vector map, you can calculate the electric field vector map. And if you get the divergence from this map, you can calculate the charge density from the divergence map in your sample as well. And that is the last thing I wanted to show you. So we have examples of virtual imaging, strain mapping, and DPC. As I showed you in my presentation, we have videos that show everything that I just showed you step by step on how you can do all of these analysis in digital micrograph on our website. If you just go to 4D STEM Media Library, and you can see those videos with your own speed. And we have the data set also available for you to download on the 4D STEM technique page, so you can play with the data yourselves. I'm gonna stop sharing now and look at the questions. Is there any questions from the room, Jordan?
Yeah, thanks, Anna. Any questions here?
Yeah.
We got one question.
On the strain mapping, it can be, on the mention, really difficult to get an unstrained area. Will the reference accept a simulated diffraction?
Yeah, so the question is on strain mapping, where you have an unstrained area. It can be hard to find an unstrained area in the same sample as a strained sample. Is it possible to use a simulated unstrained pattern?
That's a really good question. It should be possible, as I said, as long as your simulated diffraction image results into similar diffraction image conditions as you got in your 4D STEM data, then you should be able to do that, yeah. Other questions?
Any other questions for folks in person? Yeah, we got one more.
For the first demo, can you index the diffraction pattern, or can you calculate the orientation angle for the three grains?
Yes, so the question was on the example with the diffraction pattern. Can you index the different indices or calculate the angles of the different diffraction peaks?
We can measure the angle between diffraction peaks using the DiffPack tool. We don't have capability to do indexing in DM right now.
Did that answer your question?
Yeah.
Okay. Any other questions here in the room? All right, I think that's everyone on our end.
Okay. I have a couple questions online. One is, how do we know the rotation angle between the diffraction pattern and real space scanning direction? So as I said, what you want to do when you're collecting your data, you want to defocus the diffraction image and get a shadow image. And shadow image is basically you see the sample contrast within your diffraction disks, and use that shadow image, compare it to your STEM image, and measure the angle between the two. That is going to give you the angle that you need to put in the software to bring back the directions of the vectors to what you need. And then the next question is, have you already implemented Kikuchi orientation assessment using the low voltage STEM? No, we do not have that capability. I think I have seen a couple of papers where people have written their home written scripts to do that, but we do not have something similar to like EBSC and SEM for TEM in digital micrograph yet. And I think that's all. One other question, can we get 4D STEM data without a one-view type camera? We have a Orion CCD camera and a CETA camera. I cannot comment on the CETA camera, so but with the Gatan cameras, we used to have a software, 4D STEM acquisition software many years ago that would work with our older type cameras, but it only allows you to do software synchronized 4D STEM data acquisition, which is super, super, super slow. So I guess the answer to your question, if it's a Gatan camera, we will have to look at the model and how old it is, but it should be, it could be potentially possible. Of course, we recommend that you upgrade your cameras to better, more, newer technology to take advantage of all the tools that are available today. And I don't see any other questions. All yours, Jordan, I think.
Okay. Well, I guess if there's no more questions virtually, there's no more questions here in person. So I guess with that, I just wanted to thank everyone for attending today. We had a lot of fun showing everyone in person the different pieces of equipment, the different techniques. As we mentioned early on, AIF does have all of this capability. This is in Raleigh, North Carolina at NC State. They have quite a broad breadth of capabilities here. We were really happy to work with them to bring some of these new capabilities on board. So if you do have any questions about any of these techniques you saw, you can reach out to myself at Gatan or any of the folks that presented today. If you have questions about how to use this within the North Carolina area, we can also discuss that. But thank you everyone for your time. Thank you, Anna. Thank you, Fernando. Thank you, Corey. And thanks everyone for attending.